To understand the third key point, that the energy momentum tensor is a matrix of physical reality, we must shift our imagination away from single numbers and towards structured relationships. Nature, at its deepest level, rarely speaks in isolated quantities. Instead, it speaks in patterns, how one thing flows into another, how energy transforms into motion, how pressure becomes curvature, how direction itself becomes meaningful. The energy momentum tensor is precisely such a structured language. At its core, it is written as Hotaishi Jamumnu, but this compact notation hides an entire 4x4 structure. If we expand it conceptually, it becomes a matrix with Taisha Mumnu, Igam, Begin, per matrix, Taishi, and Tishan, and Chaitu, and Tushter, Itoijan, and Tushan, and Tusher, and Tushern, Iritasbet, and Tifresh, and Tishto, and Timtis, Iritaisi, and Tusham, and Totarisu, and Toshes, and matrix. Now, each entry is not just a number, it is a physical story. The first entry, Tyson Duister, is the simplest to interpret. It represents energy density, text energy per unit volume. This is the concentration of existence at a point in space-time. It tells us how much energy is stored locally, whether in matter, radiation, or fields. If the universe were a vast ocean, Taisuziraj would tell us how deep the energy is at each point. But the tensor quickly becomes more dynamic when we move beyond this first component. The next row introduces motion. The components, Fitibam's I and quad, I of 1.2.3 represent energy flow in space. They describe how energy moves through spatial directions. For example, in the x direction, title I1, man text, energy flowing in the x direction. Similarly, T2 rows and T3 rows represent flows in the y and z directions. These are not static quantities. They describe a universe in motion where energy is constantly in transit. In a complementary way, the components T, I row size represent momentum density. These tell us how much momentum is stored in a region of space, even if the system appears stationary. For instance, T per 10 text momentum density in the x direction. This is where the tensor begins to reveal its symmetry between energy and momentum. Energy flows create momentum, and momentum distribution reflects energy flow. They are not separate entities, but two perspectives of the same underlying reality. Now we arrive at the most structurally rich part of the tensor, the spatial block, Tij. These components describe stress, pressure, tension, and shear within matter and fields. For example, tau T11, T 22, T by 33 are represent normal stresses, pressures along the x, y, and z directions respectively. If you imagine a fluid, these components describe how strongly it pushes outward or inward along each axis. Meanwhile, the off-diagonal components, T by 12 darns, T 13 darn, T 23 gun represent shear stress. These describe how layers of a material slide relative to one another, like the twisting of a viscous fluid or the distortion inside a deforming solid. Thus, the tensor does not merely say there is energy here. It says how much energy is here, T series, how it moves, T E, how momentum is distributed, T E, and how internal forces behave, T E. This is why we call it a matrix of physical reality. It encodes not only what exists, but how existence behaves. To deepen this, consider that in relativity, space and time are unified. The indices for mu and IRNU each range over 4 dimensions. For mu and nu are 0, 1, 2, $3, where 0 represents time and 1, 2.3 represents spatial directions. This means every entry in Tachimuvnu is a relationship between time and space components of physical quantities. For example, Theta 1 links time, energy, to space, flow in x direction, while Theta 11 links space to space, stress along x. This mixing of time and space is not accidental. It reflects the fact that in relativistic physics, energy and momentum are deeply intertwined. One of the most beautiful aspects of this structure is that it behaves like a geometric object under coordinate transformations. If we change our perspective, rotate space, or shift between observers moving at different velocities, the tensor transforms in a precise way, preserving the physical content. Mathematically, this transformation law ensures that T shmuvnu remains consistent across all observers, even though its components may change. This is why it is called a tensor. It is a relationship that survives changes of viewpoint. But beyond mathematics, there is a deeper insight. The universe does not store energy and momentum as separate files. Instead, it stores them as interwoven patterns of flow and stress. The energy momentum tensor is the grammar of these patterns. If one were to imagine space-time as a vast living medium, then Tanja Mornui would describe its internal dynamics, where it is dense, where it flows, where it resists deformation, and where it twists. And in the presence of gravity, this matrix becomes even more significant because it is this very structure that tells space-time how to curve through the Einstein field equations. G Manu Shi Frac I APIG Gar T Manu T. Thus, the matrix is not passive, it is directive. It instructs geometry itself. In this sense, the energy momentum tensor is not just a mathematical object, it is the complete physical state of matter and energy expressed in relational form. It is reality written not as objects, but as interactions. Before we begin, it is important to understand that what we call the energy momentum tensor is not merely a mathematical object sitting quietly on a page. It is, in a very real sense, the bookkeeping system of the universe itself, the grand register in which every form of energy, every flow of momentum, every internal pressure, and every directional stress is recorded with relentless precision. To see this, imagine first a universe without such a structure. We would still have particles, fields, radiation, and motion, but no unified language to describe how all of these quantities are distributed in space and time. Physics would be fragmented. Energy here, momentum there, pressure somewhere else, each measured separately, each blind to the deeper unity beneath them. The energy momentum tensor resolves this fragmentation by compressing all of these aspects into a single geometric object. In its most fundamental form, the energy momentum tensor is written as tau ta movnu. At first glance, this appears deceptively simple, just two indices, nothing more. But those indices are not decorative. They are the coordinates of space-time itself. The index, RNMU high, refers to a direction in space-time where something is flowing, and I chnu refers to the direction in which that flow is measured. In this way, T movnu becomes a map of how physical quantities move through the fabric of the universe. To understand its meaning, we must interpret its components not as abstract symbols, but as physical realities. The component T $100 represents energy density. This is the amount of energy contained in a unit volume at a given point in spacetime. If you were to freeze the universe and examine a tiny region, T would tell you how much stuff of existence is packed there, not only mass energy, but also radiation and field energy. Then we encounter Kachos Teriskai Tausars, where I have 1, 2, 3, representing the spatial directions. These components describe energy flow, or in more familiar terms, the flux of energy through space. They tell us how energy is moving, how light streams through vacuum, how heat spreads through matter, how fields propagate disturbances across the cosmos. Conversely, the components $1, describe momentum density. This is the amount of momentum stored in a region of space, even when nothing appears to be moving in the everyday sense. For example, electromagnetic waves carry momentum even though they are massless. This momentum is encoded in these components. Finally, we arrive at the spatial components. T2, T3, stars. These describe something even more subtle. Stress. This includes pressure and shear forces within matter and fields. Pressure in this language is not merely a mechanical squeezing, it is a directional flow of momentum. If you imagine a gas inside a container, the gas molecules constantly collide with the walls. Those collisions produce pressure, and that pressure is recorded in T gauge. Thus, the energy momentum tensor is not one quantity, but a collection of interconnected physical realities unified into a single geometric object. But what makes it truly profound is that it is not merely descriptive, it is structural. In the language of general relativity, spacetime itself listens to this tensor. The curvature of spacetime is determined by it through the Einstein field equations. By G charge Jamumnu, Nafrak PIGC4 T sa Jamuvnu ta here G Jamuvnu describes the curvature of spacetime, while T Ashmavnu tells spacetime what is present within it. The relationship is not metaphorical, it is causal in the geometric sense. Matter and energy tell space-time how to curve, and space-time tells matter how to move. Thus, the energy momentum tensor is the language of influence. It is how the contents of the universe communicate their presence to geometry itself. If we step back philosophically, we may say this. The universe does not distinguish between energy and geometry as separate entities. Instead, energy is geometry in motion, and geometry is energy in structure. The tensor, Tungshamudnu, is the bridge between these two aspects of reality. And so, when we call it the accounting system of the universe, this is not poetic exaggeration. It is literal in a physical sense. Every joule of energy, every gram of effective mass, every photon, every vibrating field contributes its entry to this cosmic ledger. Nothing is lost in translation because everything is written in the same universal language of space-time indices. To truly grasp this is to realize something subtle yet profound. The universe is not built from isolated objects, but from relationships, flows, exchanges, and interactions. The energy momentum tensor is the notation of those relationships made exact. In order to understand the second key point, how the energy momentum tensor becomes the source of gravity in general relativity, we must first abandon a deeply rooted intuition inherited from Newton. The idea that gravity is a force acting across empty space. That picture, though powerful in its time, is incomplete. In Einstein's vision, gravity is not a force at all, but a manifestation of geometry itself, and the energy momentum tensor is the key that tells geometry how to behave. Let us begin with the central equation of this idea, the Einstein field equations. Frak 8 APIG C42 T Shimovnu, and this single line is the heartbeat of general relativity. On the left side stands G Shimovnu, the Einstein tensor, which describes the curvature of space-time, how space and time are bent, twisted, and stretched. On the right side stands T Shimovnu, the energy momentum tensor, which encodes all matter, energy, pressure, and stress. Between them lies a constant, dollar Ein Frak 8 API GC4. This is not a casual scaling factor, it is the bridge that translates physical content into geometric response, ensuring that the units of matter become the language of curvature. Now the philosophical leap is this. Space-time is not a passive stage. It is an active, responsive entity, and the energy momentum tensor is the script that tells it how to deform. To understand this more intuitively, imagine space-time as a vast, flexible fabric, not a material fabric in the ordinary sense, but a four-dimensional structure woven from space and time together. Every form of energy placed upon it is like a weight on that fabric, but not in a Newtonian sense of pulling downward. Instead, it changes the very geometry of distances and durations. Wherever T term of nu is non-zero, space-time reacts. For example, consider the simplest case, a region filled with stationary matter. In that region, the dominant contribution is energy density, represented by 100 time. This single component already has profound consequences. It tells space-time, here is energy concentrated in this region. In response, the geometry adjusts so that nearby trajectories of particles and light are no longer straight in the Euclidean sense, but curved in spacetime. This curvature is precisely what we perceive as gravitational attraction. In Newtonian language, we would say a mass creates a gravitational field. In Einstein's language, we say the energy momentum tensor produces curvature in G of nu kräfti, and that curvature dictates motion. Now consider something more dynamic, radiation, such as a beam of light. Light has no rest mass, yet it carries energy and momentum. This is encoded in components like tau dar and tau t I dar. Even though photons are massless, their energy still contributes to spacetime curvature. This is one of the most profound departures from Newtonian thinking. Gravity does not care about mass alone. It responds to the full structure of energy and momentum. Thus, even light gravitates and is gravitated upon. The Einstein field equations ensure that every form of energy contributes equally to geometry through Tensor movnu. This includes not only matter and radiation, but also pressure. In fact, pressure itself gravitates. This is hidden in the spatial components, TEJ in extreme environments such as inside neutron stars. Pressure becomes so large that it contributes significantly to gravitational collapse. This is not a secondary effect, it is fundamental. Pressure is not merely resistance to compression. In general relativity, pressure is a source of gravity. To see how radical this is, consider a gas cloud. In classical physics, pressure would resist collapse, but in Einstein's framework, the same pressure also strengthens the gravitational field. The system becomes self-interacting in a deeply non-linear way. The geometry responds through the Einstein tensor, tau times G a smudnu tau. This object is built from the curvature of spacetime itself. It contains information about how volumes expand or shrink, how geodesics converge or diverge, and how time itself warps. When t mubnu changes, g smudnu must adjust accordingly. The relationship is not optional. It is the fundamental rule of the universe. We may think of it this way. If t mubnu is the content of reality, then G shmubnu is the shape of reality. The Einstein field equations declare that these two are inseparable. There is also a deeper philosophical symmetry here. In classical physics, matter exists in space and time. In general relativity, matter and space-time co-define each other. The energy momentum tensor does not sit inside space-time as a guest. It actively sculpts space-time itself. Thus, gravity emerges not as a force field, but as a consequence of geometry adjusting to the presence of energy and momentum. Planets orbit not because they are pulled by invisible forces, but because they are following the straightest possible paths, geodesics, in a curved space-time shaped by T move nu. And so, the energy momentum tensor becomes the true source of gravity, not in a mechanical sense, but in a geometric one. It is the reason space-time bends, and curvature is the reason motion appears gravitational. In this view, the universe is no longer a stage where physics happens. It is a living geometry, continuously rewritten by the distribution of energy and momentum encoded in T, B, Imumnushi, while simultaneously dictating the motion of everything within it. To understand the fourth key point, the principle of conservation encoded within the energy momentum tensor, we must confront one of the deepest expectations we have about nature, that something essential must remain constant even as everything else changes. In classical physics, this expectation appears as the conservation of energy and momentum in isolated systems. But in the curved spacetime of general relativity, where geometry itself is dynamic, conservation takes on a far more subtle and profound form. The energy-momentum tensor does not merely describe what exists, it also obeys a strict rule of internal balance. This rule is expressed through the vanishing of its covariant divergence. Pornable amu t mortnu in zero tile. At first glance, this equation appears compact, almost modest, but within it lies the requirement that the universe never violates local conservation laws, not even in curved spacetime where intuition from flat geometry fails. To appreciate its meaning, we must carefully unpack each part. The symbol nabla emu is not an ordinary derivative. It is the covariant derivative, a generalization of differentiation that respects the curvature of space-time. In flat space, one might write conservation of energy and momentum as partial mu ta mufnu where partial mu is the ordinary partial derivative. This expression would mean that energy and momentum do not disappear or appear spontaneously. However, space-time in general relativity is not flat. It bends, stretches, and warps in response to matter and energy. Because of this curvature, ordinary derivatives are no longer sufficient. The covariant derivative, inabla mu, corrects for this curvature, ensuring that comparisons between points in space-time are meaningful. Thus, the equation Nabla Ermu Remuvnu height $0 means even in a curved universe, the flow of energy and momentum is locally conserved. Now, the index, our nu, plays a crucial role here. It tells us that this equation actually represents four separate conservation laws, one for each dimension of space-time. When nu jam 0, the equation becomes nabla hamu tamamu 0 $0 or ham. This is the law of energy conservation. It states that energy is not lost or created locally. Instead, it can only flow or transform. Even in a dynamic spacetime, energy remains accounted for, though it may shift between matter, radiation, and geometry. When nu Harriger's 1.23, we obtain the three conservation laws of momentum. Nabla, mu, t, mu, 1, 0, quad, nabla, mu, t, mu, 2. 0 y quad honabla mu t from u 3 from wama $0. These express that momentum in each spatial direction is also conserved, again in a local sense, but the deeper subtlety lies in the word local. In general relativity, global conservation laws are not always meaningful because space-time itself can change shape over time. For example, in an expanding universe, total energy is not necessarily conserved in the way we expect from Newtonian physics. However, the local structure, infinitesimally small regions, always obeys conservation. To understand this, imagine dividing spacetime into infinitely small volumes. Within each tiny region, the energy entering and leaving must balance perfectly. The equation Nabla guarantees this balance at every point. Now we must ask, why does this conservation law exist at all? The answer lies deeply connected to the geometry of spacetime and the Einstein field equations. G, Mumnu, and Gfrak 8 APIG, C for C, Jmuvnu, the Einstein tensor, G, Jmuvnu, is constructed in such a way that it automatically satisfies its own identity. Dan Nabla Amu G Ramujnu 0. This is not an added assumption, it is a geometric necessity known as the Bianchi identity. Because the left-hand side of Einstein's equation is automatically divergence-free, the right-hand side must also be divergence-free. This forces nabla iamu tiramuchnu tam 0 dala. Thus, conservation is not imposed externally, it emerges from the structure of spacetime itself. This is a profound shift in perspective. In classical physics, conservation laws are axioms. In general relativity, they are consequences of geometry. We may interpret this physically in the following way. Spacetime does not tolerate imbalance. Any attempt for energy or momentum to appear or vanish without accounting is immediately corrected by the geometry of the universe itself. But there is even deeper meaning here. The conservation law implies that energy and momentum are not isolated substances. they are continuously exchanged with spacetime geometry. For instance, when matter moves through curved spacetime, it follows geodesics determined by that curvature, and its motion reflects the structure encoded in T G move. In cosmology, this becomes especially subtle. As the universe expands, the geometry changes and energy densities evolve. Yet the equation Nabla Ishanamu Tishramusnu Almersi zero dilam still holds true locally. It ensures that even as galaxies drift apart and space-time stretches, no physical law is broken at any point in the fabric of reality. Thus, conservation in general relativity is not about global totals, it is about continuous consistency. We can think of it metaphorically. The universe is like a flowing river whose shape is constantly changing, widening, and bending. The energy momentum tensor describes the flow within the river, while the equation nabla r mu cha remujnu fire zero ensures that no water is mysteriously lost or created in any small segment of the flow. Even if the river changes course, the local flow remains perfectly balanced. And so, this final key point reveals something essential. The universe is not only dynamic and geometric, but also internally self-consistent at every point. The energy momentum tensor is not just a source of gravity or a matrix of physical quantities, it is also a guardian of conservation, ensuring that the unfolding drama of spacetime remains logically and physically coherent at every infinitesimal step.